Hey there, welcome to the channel. It's the Caribbean Bookworm, and if you're new here, welcome to my channel. This is a channel where I usually talk about bookish content as well as sciencey content, so feel free to stick around if one of those topics seem interesting to you. And to those who are returning, it's lovely to see you again. It's been quite a long time, and yeah, you can imagine why it has been quite a long time, but I hope to deliver on a video that is kind of returning back to basics, and that is that a few years ago I made this tier list video about courses that I took during my undergraduates. And this kind of was a bit of a quick glance as to some of the stuff that I've taken, you could say, in terms of physics and mathematics. So if you were here for the bookish part, you could say, of the channel, that's gonna have to wait, unfortunately. But if you're here for the sciencey content, especially the physics, you're in luck. So what I'm gonna do is pretty much roughly what I did in that video. So I'm gonna start by saying some of the subjects that I would like to learn, either formally or informally, but that I haven't gone about learning yet. And that is, for example, I would like to learn about stellar structures, because this is a topic that has been interesting to me like since my undergraduate years. I've really always wanted to get into the nitty-gritty detail about the physics of stars. And I have a really nice book about from Chandrasekhar on that topic that is always kind of hanging in the back on my shelf that I might use for that in sometime in the near future, in like a future summer or something. Or I might get a less rigorous book to do so as well. I'll wait and see. But that is a topic I would really like to learn. There's also the topic of gauge field theories that I would really like to know. And this is kind of basically using the physics of quantum field theory, which I'm going to talk about for sure very soon, to describe the standard model. It is basically how you learn about the standard model in the most rigorous way possible, how you get to particle physics. I really want to learn this because in the courses that I took in my master's, you learn a heck of a ton of detail about using this framework known as quantum field theory, but you don't always see, you could say, it building and converging towards the thing that it was originally created for, and that was the standard model of particle physics. So you get pieces of it, but you don't get that full narrative picture. And I really want that. Even though I don't want to do particle physics, I do want to kind of see how the standard model is built. So I definitely want to learn about gauge field theories for reasons that maybe I'll hint at a bit more later on. And I'd also like to learn string theory. And this is one that I would like to take on in a formal like course. That is because one, the institute that I am doing my master's at is quite well renowned in terms of string theory, and they have a really good lecturer for it. So I really want to make the best out of that opportunity. But also because in and of itself, it is a very interesting, you could say, framework. There's a lot of controversy, of course, around it. But the more I learned about both relativity and especially quantum field theory, the more I notice how almost natural it seems like that you progress towards something like string theory. The reasons for that is very technical and very nuanced, but if you're curious, ask whatever questions you have and I'll try to elaborate on that in the comments. And let me think if there is another thing that I would like to take, like another course. I think I've mentioned most of what I want to do, so yeah, let's actually jump into the tier list. Okay, so the way I'm gonna do this tier list is kind of in this like S tier to like something like E or F tier, and of course you can imagine that S tier is the highest, A tier is the second to highest, and so on and so forth. The lower, the worse, basically. So the first course that I have lined up are actually a set of two courses. I'm just merging them into one, and that is the course that I had called Condensed Matter Theory Part 1 and Part 2. These were both courses that I took overall in my first semester. And both of these courses were very interesting, and they were about, in essence, the basics of solid state physics as well as some add-ons to those basics. So, for example, if you took a solid state physics course in your bachelor's or in your undergraduate, I didn't, but if you did, then you would learn, for example, the basics about crystal structures and how you need to kind of analyze the energy levels in crystals. Like, say, if you have a really solid material and you're doing some experiment like X-ray diffractions, then the way at which the X-rays scatter off from the atoms or nuclei of these crystal structures can leave a certain, you could say, very distinct pattern that when you take that pattern and kind of do some fancy signal processing tricks on it, it can tell you information about the 3D array of the lattice. And that can be very informative for both practical reasons as well as just more fundamental research reasons, like learning about how materials kind of crystallize depending on external conditions and whatnot. Super interesting because the course that I took kind of added more to that basic narrative that you get typically in a first solid state physics course. We learned, for example, about the quantum mechanics behind many body physics, like what are some models that you can use to describe many body physics, and we particularly focused on conductivity and magnetism. Like these are two of the big things in condensed matter physics, two biggest phenomena that you're trying to describe, and also the idea of emergence. So the course was kind of because all theoretical physics master students, in essence, in my program needed to take both a core or courses in quantum field theory and condensed matter theory in their first semester. And I think the reason is that with quantum field theory, of course, you learn some of the tools needed to describe things like particle physics and things in high energy physics. And with condensed matter physics, you learn, of course, things for solid state and condensed matter physics. But I think also it is interesting because in quantum field theory, you think in a very reductionistic way, like you try to break things down to, like you could say, the fundamental constituents that make up like some interesting physics, whereas with condensed matter you're kind of digging in the sum of different parts to describe some new behavior that you wouldn't in principle see from the different parts in it of themselves. So you study a lot about emergence basically, and I think this was incredibly interesting because it kind of was an eye-opener to me in terms of like respecting the different ways of approaching like physics. That reductionism isn't the only way that it can be relevant, but emergence can also be extremely interesting. I already had a bit of an anticipation for this course due to having read the biography about Philip Anderson like right before I started my master's, and I would highly recommend that biography, by the way. It's extremely good. But yeah, that kind of made me already excited because I was already anticipating learning about superconductivity and whatnot. That's exactly what happened in this course. So at the end, after all that yapping, I would give this course a healthy A tier. I would give it an A tier because I don't think it's an S tier. Like it's still not my favorite subject in physics, but it was extremely valuable. And also, it's a low A tier because my course experience with it wasn't the best, like lecturer wise and everything. But I'm not gonna judge the material based on the teaching experience I had, like from my lecturer. Like in and of itself, it was very valuable. So after that, we have quantum field theory. Quantum field theory, part one and part two. This was again in the full first semester. Now, quantum field theory was quite an experience, I would say. I don't think I was ready for it. In it that it starts out very nice, so like in the beginning, it started out recapping stuff from quantum mechanics that you're supposed to know, and you kind of front load into like seeing where you could say standard quantum mechanics breaks down and why you need quantum field theory. That was kind of what the first part of the course was about, and like also getting very quickly to Feynman diagrams and perturbation theory. It's a whole lot, and that goes for the second part of the course as well. So both QFT 1 and 2, the way I would summarize it is it was overwhelming. Like also in part because of the teacher we had. He taught in a very non-traditional way, to say the least. So that didn't make for the most friendly, you could say, experience. Like it was, I remember putting in a lot of time for QFT and it was a lot of stress. So, again, if I were to be subjective, like because of that, I would put the course not in the highest of rankings. But if I were to be objective, like the course, the topic is extremely interesting. Like it was making me appreciate quantum mechanics a lot more because of how intricate you could say the details can get. And also about the course itself, our lecturer did have phenomenal exercises. It was one of the first times I remember saying that, oh, I actually really like exercises in a course. I remember really liking the course for that, and just also generally, I learned a heck ton of, you could say, new math, or I would say not learn, but I got to utilize a lot of the math that I've seen kind of in passing before. Like I had to actually use stuff about the Fourier transform of the Dirac delta function a lot. I had to use some of my complex analysis every now and then actually in like practice, like the residue theorem and doing contour integrals and whatnot. So it was kind of fun to see these things actually being put to use, and especially with complex analysis, that was a thing that I kind of taught myself. So I kind of like QFT 1 and 2 for that, and for that it goes on to the A tier as well, right next to condensed matter part 1 and 2. So after that, I didn't take more condensed matter courses because I kind of already knew that I wanted to do more like quantum field theory and kind of go the high energy physics route. So what I did was then I took a third, you could say, course in quantum field theory, so QFT part 3, and this was a 1 month course. This was in January. You can imagine how intense that must have been, but in principle, though, it was definitely one of my favorite courses throughout my master's so far. Like QFT3 was extremely fun and interesting. So after you've gone through the slog of learning how you need to care about the details of the basics of QFT, like Wick's theorem, Feynman rules for both scalars and spinor fields, and yada yada yada. These take days off and you say, what if I have a situation where I'm trying to calculate some particle scattering processes, like two electrons like scattering off of each other, and I want to take not only just the three-level contribution, which is like the simplest contributions, the simplest case you can consider of two electron scattering, but also quantum corrections, which are things that you can get by perturbation theory. So extra things like loop corrections, if you think in terms of Feynman diagrams and whatnot. And the interesting bit comes from this, that you start getting these so-called UV and IR divergencies. You basically, when you're doing this calculation, when you're predicting the probability of two things scattering, when you're calculating scattering amplitudes, you need to do some integral that integrates over all, you could say, the possible intermediate states, and doing so for all different, you could say, energies that you can have in the process. The lowest of energies, which is like the largest of distances, so what happens when these electrons are coming in and starting to feel each other, you integrate over set long distances all the way towards the shortest of distances that you can. And you notice that when you're kind of thinking about quantum corrections, that there are going to be these infinities that pop up in your calculations. And you don't like that because, in principle, these corrections are supposed to be adding to something that should be finite and physical, something that you actually see in a lab. Like what these extra corrections and quantum correction corresponds to is in reality like extra digits of precision for how accurate you can measure something happening. So like, I don't know, the 13th digit, you could say correction to some, you could say, quantum process. So the fact that you have infinities popping up in a thing that is otherwise physical is kind of problematic, and this is what QFT3 was all about. It was teaching us the techniques of regularization, which is a clever way of kind of writing out this integral over all the possible energies in a way that kind of separates the part that is infinite, the part that is blowing up, versus the part that is finite. And you also have to learn about something called renormalization, which happens after you regularize something. So after you split the infinite part from the finite part, you write your theory down in a very clever way such that you can have that the infinite part has a counter infinite part that cancels it, making sure that the finite part is the only thing that remains. If this bothers you, it is very understandable, because this is something that even people like Paul Dirac famously disliked, because he did not like the idea of renormalization and canceling out infinities just as you see fit. But the unfortunate reality of the world is that it works. It actually like gives us results that are measured in collider experiments up to high digits of precision. People can predict things using this like notion of renormalization. So it was extremely fun to learn about this, even though it is a lot of work. Like the calculations for that, I'm going to show you a picture. It is so detail oriented. It is so annoying at first. But it is kind of nice nice. Like once you get the final answer and once you kind of see this beautiful, like coherent thing, and plus also just knowing that you're able to do something like that is kind of really cool. It's kind of that thing which you imagine maybe if you thought about maybe doing theoretical physics when you were in your undergraduate or late high school, you wondered if you can do these really complicated calculations and whatnot. And in quantum field theory, especially when you're doing renormalization, that is one of the really nice examples where you are doing some of these very like intricate calculations with subtle tricks, and the fact that you can do it, I think that's a really cool thing. So for me, this course was an S tier for sure. I liked learning about renormalization, and I also liked learning about quantum electrodynamics at the end. So after QFT3, the other course that I took in my second semester was this course called Advanced Quantum Field Theory. And Advanced Quantum Field Theory was about kind of making that picture of renormalization that we just saw a bit more firm, and also getting us to think about energy scales. So I mentioned earlier how you can think of, for example, physics at the very long distances and physics at the very short distances. The jargon typically used is the infrared physics, which is a jargon because the wavelength of light that is really big usually goes in the infrared spectrum, and the wavelength of light that is very short usually goes in the ultraviolet, you could say, sector. It is not really about light when you could say physicists use the jargon of infrared and ultraviolet in quantum field theory. It is more of an expression to say things that are in long distances versus things that are in short distances. So the really interesting thing that you get to think about in advanced quantum field theory is how actually things that are affected by renormalization are actually affected by the IR distance scales, so the very long distance scales, all the way as you shorten things out down to the UV distance scales. So how is the physics of something affected in essence by the energy scales you're considering? That might seem a little bit abstract. What it means is, for example, things like the mass of something that you actually physically measure and see, or their electric charge, or even the strength of the interactions between particles. These things can all be affected by the energy scales which you're probing in an experiment, like whether you're colliding things at, you could say, the kilo electron volt, you could say, energy scales, or whether you're colliding them at the tera electron volt energy scales. So it is pretty interesting to see this, especially as we got to this topic of renormalization group flow, which is kind of telling you how the strength of some fundamental interaction can actually change depending on the energy scale you're looking. And this is pretty cool because it shows you directly how going to higher and higher energies can, you could say, make certain different types of forces, for example, like the strong, like the electromagnetic and weak force kind of slowly converge towards one, you could say, unified force, and that is the electroweak theory. So this is a direct result of this idea of the renormalization group flow, of studying how the coupling strengths between particles and their interaction kind of change as you go down towards higher and higher energies, or shorter and shorter distance scales. This kind of nicely ties into the picture, I think, in cosmology as well. It gave me a really good intuition as to why people think that when you go a bit further back in time and closer to the Big Bang, why particle physics that people do at CERN should really be telling for us, because the whole idea is that the universe was much smaller back in those early times. So if you're going back further and further, then you're getting smaller and smaller distances, higher and higher energies. So you inevitably get that if forces were, for example, unified, then that there's a unified, you could say, description of forces in the very early universe. So you could say basically close to the Big Bang, you didn't have just the electromagnetic force or just the weak force, but you had the electroweak force. And actually a bit in shorter distances, you also have that the electroweak force was unified with the strong force, the thing that keeps like protons and neutrons together. That is the so-called grand unified theory. And possibly, if gravity could be unified with all of this, you have a so-called theory of everything. So that's kind of, it slowly started showing us how you get to these ideas that you hear often in popular science, but actually rigorously. So it was really cool. I think that with all the gushing that I did, I would put this course into like an S tier, and I would be very close to doing so, but it would be a bit dishonest from me because I haven't, you could say, completed the course too early because I kind of decided to not take the exam at the end and kind of like do that a bit afterwards because I was a bit overwhelmed during this time. But that meant also that I didn't learn everything from the course, and plus the course didn't stop at the renormalization group flow. We also did a little bit of something called conformal field theory, which is a very specific type of quantum field theory that has certain symmetry properties, namely symmetries of scale invariance, that basically the theory looks exactly the same whether you're looking at very long distances up all the way to very short distances. And this is kind of very important for some condensed matter systems as well as especially string theory. But I didn't learn that part properly, to be honest, and yeah, I can't say much about the full thing. So I would put the course into A tier because I really liked things about the renormalization group flow, but I can't say in totality that I would know everything about the course. Now, aside from that course, I'm gonna go back a little bit into my first semester, and in there I also took general relativity. And general relativity was my favorite course, I think, throughout all of my masters. I really liked it, and I think it shouldn't come as a surprise, especially if you've been here for quite a while. I really like general relativity. It is the subject in physics that I think, the most comfortable intuition in. That doesn't mean that when I try to do exams and whatnot that I'm the best, you could say, exam taker of GR. I don't think so at all. But I am very comfortable visualizing stuff about GR and talking about it. And the course that I had and the course experience that I had really reaffirmed my joy for general relativity. It is one of those courses that while you're doing the derivation, the physics is clicking more in your mind. And you're also able to imagine things even better, like as you're revealing bits of the physics with your math. So I really think that GR, like back then I already thought it, but now with a bit more authority, I can claim it, that I really think GR is one of the most perfect, you could say, theories in physics. I really stand by it. Like it is very self-consistent, nice. Well, it has places where it breaks down, but it predicts those places where it breaks down, which I think is really cool. And also generally, it is just so beautiful to learn. Like solving the actual things and getting realistic descriptions is incredibly messy, and people often need computers to do it. But I think the idea and the general presentation of it extremely beautiful. I love GR S tier immediately. The other course I took was cosmology, and this I took in the second half of my first semester. And cosmology, this time actually around, I can even say the ranking already. It goes into B tier. And that's not because I like cosmology any less than I did in my undergraduate. I guess it's more part disenchantment compared to that first time I learned it. Like the first time I learned it, it was super special. And ever since then, like I've been reading about cosmology a whole lot, even like prior to me having taken that course. And also the presentation I had from the lecturer for that course wasn't, you could say, as engaging as the one I had from my undergraduate lecturer. So cosmology was really just something that I felt like I needed to do. But I still put it in B tier because, of course, it is interesting. And I think a thing that I really liked from cosmology is that because I saw a lot of things a second time around, it meant that some things could have clicked better in my mind compared to the first time I've seen them. Like, for example, the thermal history in cosmology, like how you could say atoms formed and yada yada yada, like how certain like forces decoupled and what type of radiation was first produced, yada yada yada. That stuff was never entirely clear to me because I didn't honestly care as much about it. It is often, I think it is interesting physics, but it is often a lot like, for example, dark matter to me, which is like, I know it is interesting, but I personally am not as excited about it as I know that some of my friends are. And that's okay. Different people are excited by different things. But actually, this time around in cosmology, I was actually able to internalize some of these things from other areas that are not, for example, like inflation or dark energy, that I also care about. So I think that was, I think, the main value of cosmology. Okay, so besides cosmology, I also had to take, this was one of the mandatory courses that I had to take, a course called Non-Equilibrium Statistical Physics. And this was also in January. It was a 1 month course similar to my QFT Part 3. And it was in essence a course about how messy, you could say, the thermodynamics of systems that are not in equilibrium can be. And this is basically, typically in thermodynamics, you assume that things want to thermally equalize, right? Like, for example, if I have a room that is quite, you could say, shut down at the moment, and that has, you could say, a lot of warm air, whereas outside it is really cold, then if I were to open a window, then basically the warm air would escape to the outside because it wants to go where there's less heat. And in essence, the temperature of the room would also be lowered, whereas the temperature of outside would also be raised a little bit. Things basically want to thermally equalize. And we typically assume that whether we think about it or not in nature. And this isn't often the case. Things can often be way more messier, but also way more interesting. And this is what my course on equilibrium statistical physics was about. It was about learning both in theory, but also with some computational methods, how to kind of simulate systems that are inherently in non-equilibrium. And this basically, to be more clear about it, are systems that are more subject to randomness, to stochasticity, if you will. So, and this isn't just, you could say, physics. In physics, you have examples, of course, like the diffusion of gases, even. Like, you can describe that really nicely using equilibrium statistical physics. But if you look at certain temperatures and certain, you could say, viscosities of your fluid or whatever, you can inherently run into systems where that have, for example, turbulence. And turbulence is inherently a chaotic thing which you cannot basically predict completely from initial conditions, from first principles. It goes around in very chaotic, literally, ways. So that is an example of a non-equilibrium system. And I think the coolest bit of, you could say, this aspect of physics, even though, to be honest, it wasn't my favorite course, but the thing that I found the most useful is that it seems like a subject in physics that you can almost directly like apply outside of physics. There's always the thing that can risk sounding condescending about physics students and like physics in general, and that is like physicists thinking that they can kind of jump in and do, I don't know, biology and like economics and some aspects of engineering and whatnot, and that they think that because they do physics, they can kind of plug themselves into these different domains. Of course, this is a very non-true thing, and I think that people that think like that needs to have their ego checked seriously. But there would be value to physicists trying to collaborate in an interdisciplinary manner with people from other disciplines, especially if they're looking at systems that are inherently complex. And complex, I mean it in the scientific sense. Like there's a really proper, nice way of categorizing complex systems. And this, I think, is something that would make physicists that know a little bit about stochasticity and non-equilibrium systems to be of high value in these fields, because biological systems are inherently very complex. In chemistry, you also have a lot of complex systems, and even in things such as population, like urban developments and whatnot, and especially economics, like the stock market, you have complex systems. So there's a really interesting niche there for physicists to kind of apply themselves. And there aren't a lot of people doing that yet. So it's like the thing that I have the hunch that it's going to be like machine learning, that it's going to take off very, very soon. But at the moment, the hype is only partially there, and even then, mostly among academics and in university. But it hasn't kind of spread itself out yet. But I have the feeling it will soon. So yeah, I put this course on a high C tier because I mean it was 1 month. I couldn't take much out of it, and it was brand new to me. So they didn't have the time for it to cement a little bit for me to kind of like it a little bit more. And plus, presentation wise, again, it was quite dry. So yeah, I unfortunately have to give it a C tier, but a high one at that because I noticed it is very valuable. Now, after that comes the course that I took, Mathematical Methods in Theoretical Physics. And this was a course I took in my second semester. And in essence, it was a bit of a crash course in topics of topology, differential geometry, and algebraic topology for physics students. And this, in essence, was, I think, the most formal math course I took. I didn't have to prove things and whatnot, but it came quite close to it, like the way that the literature, the presentation, and just generally the way I had to think was a bit more closely aligned with that of a mathematician in this course than it was with how I think typically about physics. Less intuitive, less quick and dirty, even though with physics already you have to be careful sometimes. But what I mean with quick and dirty is that even when the mathematics is a bit more intricate and nuanced, like with general relativity or with quantum field theory, you often can get away with things by just brute forcing, like by just writing down and like just going with it. Like it's tedious, but you can kind of get to the place you want to go by doing that. With mathematical methods in physics, especially with the ideas presented in it, I often had to be very careful and think about, oh, what does that definition that I saw imply? What does that lemma that I saw imply? And how do I make sure that I'm still logically consistent? Like, it is not a very natural way to think unless you have done stuff like pure mathematics already. I did like it though, because some of the topics after like kind of dealing with some of the formalism were actually very interesting, like even in terms of like have building up a geometric intuition. Like topology is a lot about studying spaces and studying, you could say, features from spaces that remain invariant even if you change the space. So things that basically stay the same about that space even if you morph it around and change it. And this is, for example, if the space has a hole. So if the space has a hole in it, so just a place where you don't have anything of that space surrounding it, then if that space itself is compact, so basically it doesn't extend like a full plane onto infinity, if that space is compact, then a space with a single hole can be kind of morphed in a continuous and smooth manner into other types of shape that can also, you could say, have that same property of just having one hole. So this is the famous example of the teacup being the same as a donut. We say that a teacup is equivalent to the donut up to homeomorphism. And you learn a lot about ways that you can classify, you could say, things that remain the same for different types of spaces, or in principle, different types of topological invariants. And this kind of ties at some point also a little bit to group theory, like studying how you can link the language of topology to the language of groups or sets of transformations or matrices that you can apply that obey certain axioms. And it becomes very abstract, like at some point. But it also gives you some tools to deal with some of the deepest corners of theoretical or mathematical physics, such as studying gauge field theories, which I talked about in the beginning of the video. There are very profound ways that which you can use these tools to probe the structure of gauge field theory and finding out, you could say, fundamental truths, even of physical laws, without actually having to do a lot of experiment. By just making sure that the theories that you have are consistent, you can kind of arrive at some of these very fundamental, you could say, truths about nature. I think the best example of this is the classic Aronoff-Bohm effect. This is a famous example where if you have an electron that is moving right across a solenoid that has a magnetic field, then that electron's wave function, since you describe the electron using quantum mechanics, can kind of gain an effect because of the magnetic field of the solenoid. This isn't like the Lorentz force kind of pushing the electron in a direction. This effect comes from more subtle effects, that is basically the magnetic vector potential, which is like the vector field which you can describe the magnetic field by due to taking its curl. And this is a property of having a field that is divergentless. So it is a multivariable trick in classical electromagnetism that you typically don't think about. You think about this vector potential as just a throwaway thing, but the whole gist about the Aronoff-Bohm effect is that in quantum mechanics, that A thing isn't just a metric. It actually affects physics. Like it affects the interference pattern that an electron can produce when doing something like the double slit experiment, but with a solenoidal placed in front of it. So it's pretty cool, very nuanced, but using topology, you can come around to the same conclusion without worrying about, you could say, like weird things that you can get from the interference pattern of electrons. You can just get to it by arguments of topology and the mathematical structure of quantum mechanics. It's incredible. And of course, there's a lot of geometry stuff that I took in that course as well, like formally learning a little bit about the stuff from general relativity again, as well as a little bit beyond that. So this course gets a high A tier to me, almost S tier, because of how useful I thought it was. And lastly, the last course that I want to talk about that I took is, or the pre to last one, is one called Gravitational Waves. And this course was in essence almost, you could say, a bit of a follow-up from general relativity. It was a course that showed us, well, about gravitational waves, like how they're detected and where they come from. What are the things that produce gravitational waves? And gravitational waves are of course very exciting because they're like this new window for doing astronomy. Like instead of looking at optical telescope, X-ray telescopes, and other types of different wavelengths of light telescopes, gravitational waves are just, you're literally looking at disturbances of the fabric of space-time, and that can tell you a lot about black holes, the other types of compact stars, and even perhaps physics that we haven't discovered yet, like things close to the Big Bang or exotic objects like cosmic strings and many other types of things. So gravitational waves is extremely exciting for that reason, because there's a lot of these experiments being built as we speak, and yeah, that's why I wanted to learn about it. The course experience I had itself was not my favorite, I would say, to be very blunt. The first half of the course was basically a lot about instrumentation, which I was anticipating, but I wasn't anticipating how boring I would find it. It reminded me a little bit of my physics labs from my undergraduates. Like it was about a lot about interferometers and about signal processing, which again, it's kind of cool to see these things and know that like they exist, but I really wanted to learn a little bit more about how you calculate gravitational waves, like how you predict them from some source, and how the source you're considering can affect the wavefront of those gravitational waves. We got to those interesting bits all the way near the end of the course, so it was all the way near the end of the course that I got the thing that I was personally actually quite looking forward for. So for that, I would put gravitational waves in the C tier. I still don't think it's a bad course, but I wanted something else from it. So yeah. And the last course that I will be talking about is the course I took in the last, you could say, month of my master's. Like it was a 1 month course, just as the QFT3 was. And this was quantum field theory in curved space-time. And I absolutely love this course. This next to GR was my favorite course because it really was about doing quantum field theory, but instead of considering a flat space-time background, which you usually do, like if you think about particle physics, for example, you don't think about the space-time being curved, or you don't think about gravity, because particles are so tiny that even if you were to use Newtonian gravity, like basically the gravitational force between two particles would be roughly zero because of their extremely tiny masses. So that's why you usually don't think about gravity on those small distance scales, and why usually in particle physics you do particle physics on a flat space-time background. But what if you're close to something like a black hole, or even weirder, like close to the Big Bang singularity? Then you kind of have to worry a little bit about the structure of space-time, because even if the curvature of space-time isn't something that drastically affects the gravitational pull between different particles, the fact that you have things like horizons, like causal horizons, such as the event horizon, for example, so literally regions of space-time that remain trapped after some distance, and that things that lie on the other side of that horizon cannot communicate to it, then things get a little bit weird. Because if you think about things in terms of quantum field theory, then you constantly have particles being created out of nothing, created and destroyed out of nothing. So if that were to happen, for example, close to an horizon, and that horizon traps things causally inside it, then you'd have that particles would be created near that horizon, but they would never come close to annihilate each other again. And that's how you can get very interesting, odd, weird effects coming from studying quantum field field theories in a curved background. And yeah, I really like this. Like, I could talk on and on, but for the sake of time, I won't. Absolutely liked it because in this course we derived historical things about, such as the Hawking radiation, that famous thing that Stephen Hawking is in principle well known for, and that is predicting that black holes are not eternal. They're finite, they have a temperature, and they shrink as they radiate away. And seeing how things about black hole thermodynamics lead to, you could say, open questions at the moment about things like the black hole information paradox, or questions about quantum gravity. Like, it was the course where I slowly felt that I was reaching the point where I could actually kind of sensibly talk about what quantum gravity is aiming towards or aspiring towards, since in essence you hope that something like quantum gravity is able to predict the stuff that you get from something like quantum field theory in curved spacetime, because that is like the lowest order approximation of trying to do something like quantum gravity. So it was extremely interesting, and also it led to me understanding a little bit more about the idea of cosmic inflation, which I'm already quite interested in, but seeing that derived in its more formal sense. So pretty cool stuff. High S tier for that course, and yeah. So I guess that makes the tier list, and I hope you enjoyed that. And I look forward to seeing you guys soon. And let me know if you've taken some of these courses yourself, what you thought about them, and let me know if you have any questions about other stuff. I'll see you hopefully soon.